Hello everyone. Uh, I'm excited to be here to talk about Ruby and WebAssembly, which is my main focus for past few years. So I will explore how this combination opens up the new possibility for running Ruby on a range of platforms, from web browser to edge computing. So today I will show you what you can do with Ruby on WebAssembly. So let me briefly introduce myself. I'm Yuta Saito, a master student from Tokyo, Japan. And I'm committed to C Ruby and Swift and working on WebAssembly support for both languages and mainly working on the back-end stuff in the compiler and toolchain. I'm also obviously the creator of the Ruby.wasm project. Have you ever heard the project? Raise your hands. Oh, nice. So today I will start with a brief introduction of Ruby.wasm, and then I will show you some showcases of running Ruby on WebAssembly. After that, I will explain a bit about the technical details of the project. Finally, I will share the future vision and roadmap. So, WebAssembly is a game changer when it comes to the program distribution format. Some of you may only heard the name, but first of all, WebAssembly is a specification for an instruction format designed for stack-based machine. You know the stack-based machine thanks to the last Koichi's presentations, of course. But as the name suggests, it was primarily designed for the use on the web. The main design goals are to be independent of architecture, the underlying architecture, and the platforms, and it makes it possible to port the program into every platform, and also to be efficient in terms of the size and load time, and to be able to safely execute untrusted programs provided by third parties. So even though it has web in its name, there are several runtime implementations outside of the web. The most well-known one is WasmTime, which is written in Rust language and is very fast runtime. And there are also Wasm Micro Runtime by Intel, which is made to run WebAssembly in resource-limited environments like IoT or embedded systems. And actually, there are some products that ship the runtime in a very small embedded camera system to control their runtime behavior by writing a small configuration script. So there are many other runtimes as well. Since the WASM specification does not demand a lot from the system, and all these runtimes are easily to be embedded in applications. And in addition to its embeddability, WASM also limits access to the host system. So it's useful for systems like that needs to take untrusted programs as an input from users and execute them in a safe way. Example of such application includes some plugin systems, serverless platforms, and so on. So WASM has a lot of potential as a format for sharing programs. not just for web browsers. So, for example, from the perspective of programming language, if you can compile a language to a WASM, your program can run in all kinds of environments, whether it's on ARM or x64 processors, or even on a bare metal system. On the other hand, from the platform perspective, if it compiles to the if it supports WASM, it can indirectly support many different languages without any explicit support. So that's why I think just like JSON has become a default standard for exchanging data, WASM could become the default standard for sharing program. So to take this idea further, I think we are seeing a trend where developers can focus more on their applications without infrastructure. For example, before the container era, when you really need to package up the you need to package up the entire environment into a virtual machine image. But in many cases, as long as the file system and processes are isolated, using something like Docker container is enough. And now there are cases where we don't even need full file system access and want to minimize the attack surface. You might need to handle basic tasks like computation or just reading files and writing files. In those situations, instead of container image, a portable application binary like a WASM makes more sense. Of course, this does not mean replacing everything, so it just gives an option to do a simple task in a simple way. So WebAssembly is a good, cool technology. Then what is Ruby WASM? First of all, Ruby WASM is a project that enables running Ruby on everywhere by WebAssembly. Note that everywhere is not limited to web browser, but also includes non-browser environment, as I mentioned earlier. And this project consists of three main components: CRuby interpreter compiled to WebAssembly, a packaging system for Ruby files, and an interpretation library for JavaScript. So let's see what it looks like. This is an example of running Ruby on web browser using ruby.wasm. You can run Ruby code in a script tag in an HTML file. You can call JavaScript functions through the interrupt library. You can await JavaScript promises magically using await method. So you can write asynchronous code in a synchronous way. And this is an example of running very simple Ruby on our standalone WASI runtime. We are distributing our precompiled Ruby interpreter as a single WebAssembly binary, so you can just download the binary and run it with a WASI runtime in any platform. Okay, so you saw the basic usage of Ruby WASM. Now let me show you some showcases of the advanced capability of Ruby WASM. So here is IRB is working on browser. You can access the website and try it yourself. And recently, we integrated Xterm.js to offer full-featured terminal emulations. So it it can autocomplete the suggestions and even can play the Easter egg hidden in the IRB. And another example is a Mastodon running on browser. Do you mean? Do you? It might be crazy for you, but all things running in browser. First, boot the Rails app. So as you know, Mastodon is a popular open source application that is built on Ruby on Rails. It uses a quite large, it's a quite large Rails app and includes many gems, including C extensions. So it's a good example to show the quality of our gem support. So it works. It supports the device gem, of course, and you can see some of the Rails logs in the browser console, and you can post a tweet on browser. So it works active record, of course. That's it. So this is the architecture of this demo. The Mastodon app is built on top of many gems, including Nokogiri, Haml, Active Record, of course, Zeitwerk, and many others. And some of them, like Nokogiri, includes C extensions, but as you may know, C extensions brings many difficulties. But we can now run them on WebAssembly. So the Rails app runs on Service Worker, and it intercepts the network requests from the web pages. Then the app responds those requests through the rack interface. And the app runs Postgres inside the browser too, and it communicates with the active record. So all things running inside browser. Also, you can find more examples given by the community. The first two are good example for as a playground of the Ruby on browser. The first one is quite simple, and one shortly introduced in the last Koichi's presentation to show the ISEC in the browser. And the second one is a very good integration, has a very good integration with Ruby gems. So you can try your Ruby gems on the website without installing anything. And the last two are good example to build interactive playground to demonstrate your gems. So please check their good blog post later. They describe how they built their playground step by step. So it might be interesting for you. You can you can take photo, yeah. Okay. So now let me explain the technical detail of Ruby on WebAssembly. But today I don't dig into too much, but let me briefly introduce the overview. So there are a few topics I will cover today. Porting C Ruby to WebAssembly, package gems, cross-compile C extensions, link C extensions, shared libraries. The first challenge is obviously porting C Ruby itself to WebAssembly. You might think it's easy because we already have a C to WebAssembly compiler and C Ruby is written in C. Actually, I had been working on porting the Swift compiler to WebAssembly in the last few years too. And so I thought it was easier than Swift because we already have a compiler, so we don't need to fix the compiler itself. So just compile CLB into the WebAssembly. So I thought that, but I was wrong. It was not so easy, and some of the features, including exceptions, fiber, and ZC, and they make it really challenging to port to WebAssembly. So we basically the porting work is basically utilizing the async file instrumentations, which is post-link optimization path provided by the binarian tools, and it enables some of the hacky way to enable the conservative DC exception fiber with minimal platform-specific hacks. However, we basically trade off the performance and code size for portability for now. So yeah, it works greatly for as an initial stage, but we need to improve it by using recent WebAssembly features and leverage them to trade back the performance and code size. You can see the details of this implementation techniques in the Ruby Kite 2 years ago, and I shared the implementation details in the presentation, so check it. So the next step is package gems and Ruby files into a WebAssembly binary. It might not be obvious to you because in WebAssembly, we need to package everything into a single binary to ship a binary as a single binary. So we made a virtual file system on the top of the WebAssembly technology. So we now have a way to package the Ruby gems listed in the gem file by using a rbwasm command, which is provided by the ruby.wasm project, and just build them using the build subcommand. Then you can get the all packaged WebAssembly binary. And the package gems are stored in the VFS. And you can set up the load path by bundler setup. Then you can require gems as usual. So nothing special here. The next challenge is cross-compiling C extensions to WebAssembly. If you want to build C extensions, you need to talk about. I need to talk about the MKMF. As you know, MKMF is a core of the C extension build system in the Ruby ecosystem. MKMF is abbreviations of makefile, and it literally makes makefile from xconf.rb. Now you have three major users of MKMF: CLB build systems, Rake compiler, and the last one is Ruby gems. Ruby gems uses it to build gems with C extensions when you use gem install. However, Ruby gems didn't have a cross compilation support at the moment, and also MKMF itself didn't offer good cross compilation support, and it forces the users to add some extra hack. So, but I don't want to introduce a new trick to Ruby gems, so I introduced the native cross compilation support in the MKMF itself. So, yeah, it will be shipped as a part of the Ruby 3.4, and also we added the support for in the Ruby gem itself. So, and it's rendered in the main branch, so it should be available in the 3.4 too. So we can cross-compile C extension to WebAssembly. Then the next step is to link the compiled library into the C Ruby interpreter. So we have two options for linking C extension to the interpreter. The first one is static linking, and the second one is dynamic linking. And usually on platforms we use dynamic linking, but however, supporting dynamic linking in WebAssembly is not obvious way. So we already support static linking for the built-in extensions like JSON or something like that. But we decided to go with dynamic linking to support Ruby gems. Why? The main reason is that the build model is not suitable for the Ruby gem ecosystem. So static linking takes a long time to link step, and especially async which is a code transformation I introduced before, is quite slow, and it had to be applied after the static link. So yeah, that was a bottleneck for the development flow. And also there are a couple of the issue in the static linking build model, and the main problem here is that we had to pause and resume the build system, and which is not a common way in the build system. So, but in the dynamic linking, we can utilize the existing workflow without any pain, development workflow pain. So yeah, that's why we tend to employ the dynamic linking. But why we didn't do it so far? The main reason was WebAssembly does not have standard dynamic linking ABI, and if we do our bespoke dynamic linking, the binary will be incompatible with the standard WebAssembly runtimes, so we lose the portability of the WebAssembly binary. So we didn't do that. However, the situation had changed recently. The WebAssembly community has been working on a new layer of WebAssembly standards, that's the component model. This model is built on top of the existing WebAssembly standards, and we expect it to be the future of WebAssembly. And the component model exists several features, including IDL, module linking, and so on. But the most important feature to achieve dynamic linking is module linking. Module linking is a new concept to build a program by composing multiple programs at the build time. The new binary format allows embedding multiple WebAssembly modules into a single binary, and it allows describing how the modules link to each other. So based on the module linking, we can build dynamic linking mechanism on the top of that. The key idea is that given the module has its metadata for dynamic linking, like symbol table and relocation information, and which modules it depends on, then we can encapsulate how to link modules into a new binary format, which is called as a component. So we can encapsulate the link step at the build time, but we can utilize the dynamic linking ABI implemented in the existing tool chain. So in this case, we have 4 WebAssembly modules, and we can bundle them into a single component ahead of time. So the ahead of time dynamic linking is a bit different from the traditional dynamic linking, and the actual linking is done at the build time, so not at the runtime. The binary is a single component, and it consists of all dependencies, and we made a linker to link them up into a single binary with a Python with a guy who is working on the porting C Python to WebAssembly, and we are working on together to make the linker. So the main difference from the traditional dynamic linking is that the final binary is a component. The final binary is fully self-contained, and the linking is done at the build time. So there is no file-based library search at runtime. Therefore, DL Open is available for only libraries known at build time, and it's not possible to inject new libraries at runtime. So yeah, that's how we implemented the Ruby version. So okay, so finally, let me introduce the future vision and roadmap. This year, I drew the roadmap for my 3 goals. The first one is binary size, and also the runtime performance and normal platforms. Because WebAssembly is very working in progress technology, so it's not a normal platform yet. So we need to make it as a normal as much as possible. And digging into the binary size, there are several optimization opportunities in terms of the interpreter design and the hack we applied to achieve some of the feature like exception fiber, and also we can apply some of the compiler optimizations to make it binary size friendly. So in summary, Ruby runs on WebAssembly, and it now supports Ruby gems, and Ruby is leveraging the state-of-the-art WebAssembly technology, including component model, and we are investing on the evolution of WebAssembly to make Ruby more WebAssembly friendly. So that's it from me, but by the way, I'm going to graduate from the university soon, and I'm looking for job opportunities, so I'm good at compiler build system and WebAssembly, and looking for position related to programming language toolchain development. So if you have any interest, please contact me. Thank you.